Good morning, my name is Alekhya, and in this video my team and I will be explaining our project titled Implementing a Digital Thermostat for Heating and Cooling, and finally we'll deploy it on the FPGA board. So I'll begin by walking you through our design code. So this is our design code which consists of 4 main modules. Let's start with the project module. This is to explain the thermostat FSM. So this module implements the finite state machine that controls the heating, cooling and fan speed based on the current temperature and the target temperature. So we have also introduced a hysteresis band of 2 degrees. So when the temperature drops below the heat on threshold, the system enters the heating state, and when the temperature rises above the cool on threshold, it enters the cooling state. And if the temperature is equal to the target level, the system comes back to idle state. So that's why we have 3 different states: the idle state, the heating state and the cooling state. So for example, in the heating state, the functionality is something like this: the heater is switched on, the cooler is switched off and the fan speed is on low. And similarly, in the cooling state, the heater is switched off, the cooler is switched on and the fan speed is in high, which is 1, 0. Now let's move on to the next module, which is our debouncer module. So since we are using push buttons to operate our heating and cooling, we need to handle the bouncing effect. So this is caused by the metals when we press down a push button. It doesn't switch cleanly and it produces a series of fast on and off pulses. So this debouncer module helps us filter out those unwanted transitions to ensure that one physical press is equal to one logical press. And that is everything about what we have coded in this module. Next, we have the button control module. So the button control module decides how the push buttons affect the operating mode. So when our heat button is switched on, which means it is pressed down, then our mode is mode off, which means that irrespective of the FSM's mode, our system should be heating. And that is why this code is written like this. As well as when the cool button is switched on, the mode should be in cool mode. So that's how we have written our functionality of our push button. And finally, when both heat button as well as the cool button are pressed down, then it should enter into our auto mode. This means that depending upon the temperatures, the target and the current temperatures, the system will decide either to cool or to heat, and the fan speed respectively. Our final module is our top module, so which instantiates all the other modules and connects them together. And this is the module that we'll be implementing on the FPGA board. So now that the design is explained, we'll look at the simulation waveform to see how the thermostat behaves under different conditions. So this is my simulation waveform. So over here you can see that T current is my 20, T target is 25, and then we have my heater, my cooler settings as well as my fan speed. So I'll walk you through a few test cases. So over here you can see that my T current is 20 degrees right now. My T target is 25, and as our hysteresis band is of 2 degrees, this means that the system should heat right now. So our heater is switched on, our cooler is switched off, and the fan speed is in low, which is 1. Let me look at another test case. So this one, where our current temperature is 30 degrees, our target temperature is 25 degrees. This means that our current temperature is higher than the target temperature, which means cooling should occur in the system. So the cooler is switched on, the heater is switched off, and our fan speed is in high. Thank you. This is all for the explanation of the code.
So we've uploaded the code on our FPGA, and these are the dip switches for the target temperature. So, and that is 8 bits, we've assigned push buttons to the physical heat button, the physical cool button, and the reset. This would be the physical cool button, this would be the physical heat button, and this is the reset button. Also, we've assigned LEDs to physical cool on, physical heat on, and fan speed, which is a 2-bit output. So these two LEDs would be our fan speed output. This is the heater output, and this is the cooler output. And also, because of hardware limitations, we've used the VIO to assign the current temperature, which is also 8 bits. Yeah, so essentially the idea of the project, as Alekhya already explained, would be when the current temperature is higher than the target temperature, then the cooler should be on, and when the current temperature is lower than the target temperature, the heater would be on. So let's try out some values here. Let's assign this to 8, the target temperature to 8, and on the VIO, let's make the current temperature 12. Yeah, so the board automatically is in auto mode initially. So since the current temperature is higher than the target temperature, the cooler is on, as you can see, and also the fan speed is set to 2 whenever the cooler is switched on. So the physical heat button and the physical cool button just forces the system to go into physical heat or physical cool respectively. So for example, if I press the physical heat button, it forces the system to go into heating. Yeah, so it's switched to heating. Now let's change the current temperature on the VIO. Let's change this to 4. Yeah, so this would mean that the heater is switched on and the fan speed is also set to 1. And of course, reset sets everything to 0.